Hello, ninth grade students. Today we are going to talk about spheres and frustums. I know we've discussed spheres so far, but what I'd like to do today is show you where the volume formula for a sphere comes from. To help us derive the formula for the volume of a sphere, we first have to talk about Cavaliere's principle. And let's take a look at this. If F and G are solids located between two parallel planes, pi and sigma, and if for every plane gamma parallel to and between pi and sigma, we have that the area of those cross sections are equal, then I know the volumes are equal. So if I look at these two cones, and I see that as I take a plane and I cut into each of these, and I see these cross sections are exactly the same all the way from the bottom to the top, what I can then conclude is that the volumes of the cones are equal. So to derive the formula for the volume of the sphere, we have to look at two figures. I have this cylinder here and a cone cut out of it, and I have a half sphere here. And just let's read through what's given so we are all clear on that. Gamma is parallel to sigma and pi. Sigma's up here, pi's on the bottom. Gamma is this plane that's in between. AC is equal to r, so the distance between sigma and pi is r long. S is a cylinder, that's my cylinder here. C is a cone with the same base as that cylinder. H is a half sphere. The distance between gamma and pi is x, so between here and here, that's x long. So what we're going to work to do is show that all cross sections of the complement of C, meaning outside of the cone, intersected with my cylinder, this donut looking object, they actually call that an annulus. The area of that annulus is the same area as the cross-section of the sphere, which would then be a circle. So we're first going to work on that. So let's take a look first at this annulus here. So it is two circles. I have this outside one and I have an inside one. This circle's radius is r. So and the inside radius, that I have to find. You can see it right there. So we're going to do that by drawing a couple right triangles. So I have this right triangle here, and I have this one here. That is part of the outside one, so this guy. And notice that these angles here and here are both right angles, and they share this angle. So therefore, I know that these two triangles are similar. So that will allow me to find this length right here. So looking at that, let's look at the outside circle and the height of my cylinder. So this radius over this length would be the same as this over that. And we know that this distance here is x. Remember, we said the distance between pi and gamma is x long. So I know that r is to r because the distance between sigma and pi is also r, is equal to x over x. So basically these are isosceles right triangles. So if this distance is x, so then is this. So I can find the area of the annulus by taking the area of the big circle and subtracting the area of the small circle. The area of my big circle is going to be pi, and the radius of that is r squared. Well, my radius is r, right? So the distance between here and here is r. the area of my small inside circle is pi and then the radius squared. The radius in this case is x. So the area of my small circle is pi x squared. The difference is what the area of that annulus is. So I would take pi r squared and subtract pi x squared. And I can factor out a pi just for fun. So that's that area of this donut-looking object. Next, let's find the area of the circle that is inside the sphere. So the radius of this half sphere is pi because the distance between pi and sigma is r. So I know that this distance here is r. We already decided that this distance between B and Q, the distance between gamma and pi, is x. So I'd like to find this radius here. Well, I can use Pythagorean theorem because I have this gorgeous right triangle. So let's call that t. So let's find that radius. T squared plus x squared has to be r squared. So solving for t squared, I get t squared equals r squared minus x squared. So I know that t is equal to the square root of r squared minus x squared. All right, so the area of that circle, that cross section of my half sphere, has to be pi times the radius squared. And my radius is t. And if I square that, I get pi times r squared minus x squared. Didn't I see that somewhere before? Look at that. So all of those cross sections are exactly equal. So now that I know that the volume of what's in the cylinder outside of the cone has to be the same as the volume of this half sphere. So now let's look at these volumes. We know the volume of the cylinder. The volume of my cylinder is the area of the base times the height. I know the volume of my cone is 1/3 the area of the base times my height. So the volume of what's outside of that cone has to be the area of the volume of my cylinder minus the volume of my cone. And that is 2/3 the area of the base times the height. So looking at this, I know that the volume of this part here has to be equal to the volume of my half sphere. But the height here is r. And the area of my base is pi r squared. So this leaves me 2/3 pi r cubed. Well, the sphere is double that. It would be 2 times 2/3 pi r cubed, or 4/3 pi r cubed. And there you have the volume of a sphere formula that I told you earlier. Isn't that fun? Next, let's talk about what a frustum is. A frustum, in non-mathematical language, is just a part of a cone or a part of a pyramid. It is a cone cut off. It is a pyramid cut off. This circular face is parallel to the base. This triangle here is parallel to that triangle. It is a frustum. So let's read the formal definition just so we're really clear on what it is, and then we're going to talk about how to find the surface area and the volume of a frustum. So a frustum is a figure in space that is determined by a measurable figure S in space in two distinct planes, pi and sigma, that are parallel, and each of which intersects S in at least one point. The frustum that they determine is the union of pi intersect S, sigma intersect S, and the set of all points of S that are between pi and sigma. When S is a circular cone or a pyramid, the frustum is called a conical frustum or pyramidal frustum, respectively. For each length u, the u height of the frustum is the perpendicular u distance between pi and sigma. So you can see here the height is this perpendicular distance right there. The planar figures pi intersect S and sigma intersect S are called the bases of the frustum. So I have a base here and a base there. I have a base here and a base there. The volume of a conical frustum is given by this formula. It's 1/3 pi times h, that's the distance between the bases, r1 squared plus r1 times r2 plus r2 squared. R1 and R2 are the radii of the bases. So let's see here. This would be R2. Hold on a second, I don't like where I drew it. R2. And this would be R1. And quite honestly, it doesn't matter which one we call R1 and which one we call R2. But that's the formula for the volume of a conical frustum. It's nice to know the formula, and it's much faster. I do want you to have some idea about where this formula comes from. You can imagine that you have this whole cone here, and if you wanted to find the volume that way, you could take the volume of the large cone and subtract the volume of the small cone. And of course, these are similar triangles. We'll do something like that when we are looking at a pyramidal frustum. And the surface area of a conical frustum is given by this formula. It is pi r1 squared, that's the area of one of the bases, plus pi r2 squared, that's the area of the other base, plus pi, the sum of r1 and r2, times s. And S is the distance, it's like the slant height of a cone, except it's just the part between the points on between these two bases. So it's part of what would have been considered the slant height. So again, that's this formula here. And while this formula is very nice, and I absolutely would use it, I want you to realize that you could find the surface area of this right conical frustum by finding the lateral surface area of this large cone here. I'm subtracting the surface area of the lateral surface area of the small cone, and then adding in the area of each of those bases. That would work as well. I'd like you to use these formulas to find the volume and the surface area of the right circular frustum. Notice that you'll have to use this 30-degree angle to find the distance between the bases and also to find S. Here's my answer. So I simply plugged into the formula, but I had to find the slant height and the height. So I used this 30-degree angle down here. It's a little bit challenging in some ways because it is not drawn to scale. So if I look at this frustum, and this is 30 degrees, and I have my radius up here 5, and this whole radius across is 8, I know this piece right there is 3. Now, across from the 30-degree angle is A, across from the 60-degree angle is A times the square root of 3. So to go from this side to that, I have to divide by 3, and multiplied by the square root of 3. So the height is the square root of 3. The slant height is 2 times that, or 2 square root of 3. So plugging into my formulas, I have 1/3 pi from here times the height, r1 squared, that's the 8 squared, plus r1 times r2, 8 times 5, plus r2 squared, that's 5 squared or 25. And when I add this all together and divide by 3, I get 43 pi square root of 3. And volume is measured in cubic units. The surface area plugged in, pi r1 squared, that's pi times 8 squared, plus pi r2 squared, that's 5 squared here, plus pi times the sum of my radii times the slant height, which was 2 square root of 3. So these would be my like terms here, 64 pi plus 25 pi, that's 89 pi, plus 8 plus 5, that quantity times 2 is 26 pi square root of 3. And that's my surface area. And remember that surface area is measured in square units. Next, I want to find the volume of the right square frustum. The problem for this is that we don't have a nice formula like we had for the circular frustum. So I have some measurements drawn on here. Now let me show you what we need to do. We have to extend the sides of this frustum up so that I can see that this really was all part of one pyramid. Now, what we'll do is we'll find the volume of the whole square pyramid and subtract the volume of this small pyramid on top. Now, one issue is that, I have to find a way where I know the entire height of this pyramid. Right now, I only know the distance between the bases of my frustum. And I also need to know the height of this one here. So in order to do that, what we're going to do is we're going to use some similar right triangles. So if I look at this right triangle here, these angles, and the angle for my large right triangle and the area for my small right triangle, they're both right angles, so those are congruent, and they both share this common vertex angle. So therefore, the triangles are similar, and I'm going to be able to use that fact to find this length. Now, I already know the length of this leg of my top right triangle, and that's because it's half the length of the square base on this pyramid. So if this side is 12, I know that this segment is 6. So now I also know further that down here, that's half the side length. So this length is 24. And now I can use these similar triangles to find the missing height of the small pyramid. So I will call that H. So using the similar triangles, H is to 6 as H plus 24 is to 24. Long leg is to short leg as long leg is to short leg. Now we can cross multiply and solve for H. So I'd have 24H equals 6H plus 6 times 24, which was 144. So I'll subtract 6H from both sides, and that gives me 18H is equal to 144. Divide both sides by 18, and I find that H is 8. And that is the height of my small pyramid. Of course, the height of the large pyramid goes from up here to down there. So the height of my large pyramid is going to be 8 plus 24, or 32. So again, from the vertex of my large pyramid down to the base, I'm looking at a height of 32 units. So I would like you to press pause on your video and complete this problem. Find the volume of the square frustum. When you're ready for the answer, press play and we'll talk about it. So here are my answers. You can see I plugged into my formula that says 1/3 the area of the base times the height is the volume of a pyramid. My base for the large one is 48 squared. Side squared, it's a square, times the height, 32. That comes out to be 24,576. Then I found the volume of my small pyramid using the same formula, but this time the area of my base is 12 squared because the side of my square is 12, times the height, which is 8. That gives me a volume of 384. And then the volume of my frustum is the volume of the large pyramid minus the volume of the small pyramid, which comes out to be 24,192. And remember, volume is measured in cubic units. Next, I'd like to find the surface area of the right square frustum. I want you to think for a minute about what you should add and or subtract to find the total surface area of this square frustum. Press pause on your video, and when you've thought about it and you want to compare your answer with mine, press play again. So what you would do is you would find the total surface area of your big pyramid. You would subtract off the lateral surface area of the small pyramid, and then you would add the base of the small pyramid, and that would cover all the surface area of this square frustum. So I would like you to find the total surface area of that square frustum. Press pause on your video, and when you're ready for the answer, press play again. Here are my answers. We were pretty lucky in that these triangles inside here were 3, 4, 5 triangles. So as I look to find the slant height for each of my pyramids, if I know that this is 6 and this is 8, this is my 3, 4, 5 triangle. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. This slant height is 10. I can look then at this triangle that's inside my large pyramid, and this length here is 32. This length is 24. So this is still my side that's 4. 4 times 8 is 32. 3 times 8 is 24. 5 times 8 is 40. So this entire length here is 40 long. From this point here to there would be then 30. So now I should have what I need. So to find the surface area of the large pyramid, I first have to find the area of the base, which was 48 squared, or 2,304. Then I found the lateral surface area, which was 1/2 the perimeter of the base times the slant height. The perimeter of my base is 48 times 4, and we already found my slant height to be 40. So the lateral surface area is 3,840. My total surface area is what I get when I add these two together. For the total surface area of my large pyramid, it's 6,144. Now we find the surface area of the base of the top base of my right frustum, or the base of my small pyramid. That is 144, or 12 squared. The lateral surface area of this top small pyramid is 1/2 the perimeter of the base times the slant height. The perimeter of my base is 12 times 4. The slant height is 10. So my lateral surface area of my small pyramid is 240. I'm not quite sure why I found the total surface area of my small pyramid. I guess I'm an overachiever, but I just added those together. Then I found my total surface area of the right square frustum. I took the total surface area of my big pyramid, which was 6,144. I subtracted the lateral surface area of my small, which was 240, and then I added the base in for this top base of my square frustum, which was 144. So my total surface area is 6,048. And remember, surface area is measured in square units. So that concludes today's lesson. I posted my assignment for you online. Today, remember, we just derived the formula for the volume of a sphere. So hopefully that will help you remember what it is and how to find the surface area of and volume of frustums. Have a nice day, and I'll see you soon.